As I was recording video 8, there was a little bit of a happy accident where I happened to stumble across a real-world chart that happened to display a behavior very similar to what we see in the graphs of sine and cosine. In particular, what we ran across was the chart of how many people are using the service Steam at any given time, the concurrent users of Steam. And this is the kind of thing that we will be studying over the next couple of days. Real-world quantities which, when charted, begin to create a pattern that looks very, very similar to the graphs of the sine and cosine functions. Goal for today is to state the definition of what is called a sinusoidal function. We're going to graph sinusoidal functions. We're going to define what's called the period, amplitude, and midline of a sinusoidal function, and we're going to identify the values of those three objects by looking at the graph of a sinusoidal function. Now, before I get into that, I want to review ever so briefly the idea of transformations of functions from Pre-Calculus 1. A transformation of a function f of x is another function that I might call g of x, which is related to f of x in the following way. G of x's formula can be found by taking the formula for f of x, potentially multiplying it on the outside by some number, potentially multiplying it on the inside by some number, potentially adding or subtracting something from the input, potentially adding or subtracting something from the output. So a transformation of a function f of x is another function whose formula can be expressed in this way, where a, b, c, and d are all constants. Now, the interesting thing about f of x and any other transformation, such as g of x, is their graphs have the same basic overall shape. If f of x looks like a parabola, then g of x is also going to look like a parabola. It's just that potentially the parabola might be wider or more narrow. It might even be flipped upside down. It might be moved up or down or to the right or to the left, but the overall shape of the graph is the same. The overall shape is parabolic in nature. A transformation is the kind of thing that you're doing when you, for example, manipulate an image in a computer. Here I've pasted an image of the basic absolute value function, and I can transform this image by, for example, stretching it vertically, or compressing it horizontally, or shifting it to the right, or shifting it up or down. All of these actions would give us something that's a transformation of the original absolute value function. Now, suppose that you're dealing with a real-world wave pattern. For example, the wave pattern that we saw in the chart for the number of users who were using Steam at the same time. Now, the default sine of x function may not be an exact match to whatever wave pattern you're dealing with in real life, but you might be able to get sine of x to be an exact match to your real-world wave pattern by transforming sine. For example, here, if I wanted to match the sine function to the yellow wave pattern that I was seeing in this chart, the first thing that I would have to do is horizontally compress it, because I noticed that in the chart, the distance between the two peaks is rather small. I also think that compared to the yellow graph below, the difference in height between the peak, the max, and the min is too big in the default graph of sine, so I might have to vertically compress this to make it match up a little bit more closely, maybe a little bit more than that. And then I might have to horizontally shift this image to make it so that the peaks are occurring at, roughly speaking, the same time. Not quite perfect because it's not letting me completely freely move this image. It's moving in chunks. But if you are able to move it completely freely and not in chunks the way that this program is forcing me to, you would be able to match up this sine pattern with this actual chart pretty closely. So mathematically, what would we have to do to the sine function that would capture this behavior that I did with my mouse of shrinking the graph vertically, compressing it horizontally, and moving it around? Well, we would have to take the formula for the sine function and we would have to figure out exactly what values of a and b and c and d that we would need to put in the input and in the output to get the height of sine to match the height of the wave in the chart, to get the width of sine to match the width of the wave in the chart, and to get the position of sine to match the position of the wave in the chart. And that's what we're going to be working on studying today and tomorrow, is how do we choose the values of a, b, c, and d to give us a sine function whose wave pattern is an exact match to any real-world wave pattern that we happen to be working with. If we can get a sine function which matches the behavior in the chart, then we can use that function to do all kinds of calculations and predictions. For example, if you were trying to set up your servers to be able to handle a certain number of people playing a game, then you can use a function like this one to predict what kind of server you would need in order to handle that many players. So the official mathematical terminology for an altered transformed sine function, the official term is sinusoidal, sort of sine-ish, sine-like. A sinusoidal function is a function of the form sine, except maybe you multiplied on the outside by a number, maybe you multiplied on the inside by a number, maybe you added or subtracted something from the input, maybe you added or subtracted something from the output. In other words, a sinusoidal function is a transformation of the basic sine function. So sinusoidal functions, as we discussed in the beginning of the video, can be used to represent any kind of cyclical or wave-like behavior, including actual physical waves in water or some other liquid. Sound waves, for example, are represented by sinusoidal functions, as well as electromagnetic radiation. Also, anything with a cyclic, predictable up and down behavior, such as the number of users on Steam at any given time, or things like the amount of sunlight in any given day. We get the most sunlight per day in summer, and then it decreases to a minimum in winter, and that pattern repeats forever and ever, or at least as long as we will be alive. Likewise, temperature, maximum in summer, minimum in winter, and that cycle repeats. A lot of physical things in the body repeat daily, such as the hormone melatonin, which controls sleepiness. Melatonin reaches its maximum, generally speaking, a few hours after sunset to make you sleepy, and melatonin is at its minimum after you have slept a full night. Now, when we are trying to match a sinusoidal graph to a real-world wave, generally speaking, it's not possible to make the match completely perfect. You can get quite close, but because stuff in the real world has a little bit of chaos inherent to it, the match will never be exactly perfect. So when we're trying to match a mathematical sinusoidal wave to a real world wave, we focus on making a few different features of the graph match the real world wave. And the first thing that we try and match is called the midline. The midline of a wave, the midline of a sinusoidal function, is the horizontal line, which is directly between the highest point and the lowest point. So-called midline because it cuts right through the middle of the graph. Now, when you're dealing with real-world waves or real-world cyclical behavior, the midline represents physically the average amount. Scrolling back up to that chart of STEAM users, the midline, which cuts directly between the peak and the lowest amount of users, the midline would cut right through the middle. So I'll sketch it in blue here. The midline on this scale looks like it's about maybe 24 million users. And this would be how many people are using STEAM on average at any given time. The midline, the average number of users, cuts right through the center of the wave horizontally. Let's identify the midline of the sinusoidal function graphed below. So the highest point on this wave is up here at y equals 5. And the lowest point on this mathematical wave is right down here at y equals -1. Now some of you might just be able to visually count your way toward the center here, but if you're ever having trouble specifically identifying what number is between 5 and -1, you can always take the mathematical average of those two, which says add the two numbers together, split the difference, cut the result in half. Directly between 5 and -1 is the number 2. So the midline in this picture, the midline would be the horizontal line located right here at y equals 2. So midline, when we're trying to get a mathematical wave to match a real-world wave, one of the things that we try and get to be exactly the same is the midline, to get the average value of the mathematical model to be the same as the average value of the real-world quantity. The second feature that we try and match when we're working with waves is something called the amplitude of the wave. The amplitude of the sinusoidal function is the distance, the vertical distance. Yes, I'll specify the vertical distance between the average, the midline, and the peak of the wave, or its most extreme value. For example, going back to that sinusoidal function that we were looking at just a little while ago, the midline was located at y equals 2. Now, how far does this wave deviate from its average? Looking at the distance between the midline and the peak, here at y equals 5, the distance between the midline and the peak, 3 units in total. So, based on the definition of the word amplitude, I would say that the amplitude of this wave is 3 units. Now, in terms of physical waves, the amplitude can have a couple of different meanings depending on what kind of wave you're working with. For example, if you're dealing with a sound wave, the amplitude for a sound wave represents how loud the sound is. If your sound wave has a larger amplitude, then you will perceive that wave as being louder. If it has a smaller amplitude, then you will perceive that wave as being more quiet. For electromagnetic radiation, the amplitude represents the strength of the radiation. For a simple example, consider visible light, which is a form of electromagnetic radiation. If you have a visible light with a larger amplitude, that light will appear brighter. If you have a visible light with a lower amplitude, that light will appear more dim. And in general, for cyclical behavior, such as the number of users on STEAM at any given time, Amplitude represents, roughly speaking, the difference between the average and the most extreme situation. On average, there were around 23 million users. But if you want to prepare your servers for the worst case scenario, you're going to have to prepare yourself for, it looks like maybe around 28 million users, roughly speaking, on this scale. So the midline was at 24 million, the peak is at 28 million, and therefore the amplitude, the difference between the most extreme case and the average case, is 4 million users in this particular example. When we're matching a mathematical wave to a real-world wave, the third feature that we try and match is what's called the period. The period of a sinusoidal function is the time required for the graph to repeat. Another way to phrase this would be the horizontal distance between peaks. So scrolling back up to that real-world example, the period of the wave displayed in this chart would be the amount of time between one peak and another peak, where the behavior that we're seeing, the pattern that we're seeing, has completely run its course and is now repeating. So based on this scale, it looks like the period would be around 1 day. Every day, the general pattern that we're seeing in the number of Steam users repeats itself. Let's have a look at a mathematical example, and let's try and identify the amplitude of the sinusoidal function, which is graphed here. So let's figure out how long it takes for this graph to repeat itself. And one way to tell is to look at the distance between the two peaks on this graph. However, because the coordinates of the two peaks are not exactly given, it might be easier to look for two other matching sections on the graph and look at the distance between those. For example, this is a location on the graph that is going upward through the midline. And I can see that the graph, the wave will run its course and it will begin to repeat at this location, which is also going upward through the midline. I'm going to have a look at the distance between these two locations, these two matching locations, simply because I can actually see where those locations are located exactly. One is located at pi and the other one is located at 0. This sinusoidal function would have a period of pi units. It would take a horizontal distance of pi units, a time of pi units for this wave to repeat. Now, what does period represent for real-world waves? Let me focus on light. The period will affect the color of the light. For sound waves, the period of the wave affects the pitch of the sound. For cyclical behavior, it's the amount of time for the cycle to repeat. So, the general process for matching a sinusoidal function to a real-life wave pattern. First, you make a chart of the real-world wave pattern, and using the chart, you write down the amplitude of the real-world wave, you figure out the period of the wave, and you figure out the midline of the wave. That's the kind of thing that we learned how to do today. How to take the graph of a wave and write down its amplitude, period, and midline. Tomorrow, what we're going to learn how to do is to come up with the equation of the sinusoidal function that has a matching amplitude, period, and midline to the real world wave that you're trying to capture mathematically. To conclude today's video, let's just finish with a bit more practice identifying midline, amplitude, and period. And to begin with, what I want to do is figure out the midline, amplitude, and period of the basic, no transformations, straight up sine function. The graph is given here below. Alright, the midline. The midline is the line that cuts directly between the peak, located at y equals 1, and the lowest point, located at y equals -1. Directly between +1 and -1 is y equals 0. So the horizontal line, y equals 0, is the midline. Next up, the amplitude. What is the vertical distance between the midline and the wave's highest point? Now the midline is located at y equals 0, and the highest point on the graph is located at y equals 1. So the distance, vertical distance between 0 and 1 is 1 unit. This is the amplitude of the basic sine function. And what about the period? What is the period of the basic sine function? Well, let's try and identify a point on the graph that's relatively easy to read. For example, we could use the lowest point on the graph, which is located here at -π/2 in terms of horizontal position. Now, if I follow the graph from that point through one full cycle, going up and back down again, when I reach the matching bottommost point after one cycle has been completed, I am now looking at the location where x is equal to 3π/2. So what is the horizontal distance between 3π/2 and -π/2? To figure that out, we can look at the difference between these two, which is equivalent to 2π units. In other words, it takes the regular basic sine function 2π units in order to repeat. That's actually something that we've had a brief look at before. The sine function repeats every 2π units. Now, I just decided to look at the period by comparing the distance between lowest points, but you could also figure out the period by looking at the distance between the peaks. Or you could figure out the period by looking at the distance between any other two matching locations on this graph. For example, one nice choice might be to look at the distance between this point, which cuts through the midline going upward, and this point over here, which also cuts through the midline going upward. You could also use these 2 points to determine the period, and you could also find out that there's 2π units between those two matching locations as well. Regardless of the method that you use, we find that the midline is y equals 0, the amplitude is 1 unit, and the period is 2π units. That is what's true for the basic sine function. Now let's try it with a transformed sine function. Let's try it with the sine function where we've multiplied on the outside by -4, we've subtracted 3 on the outside, and we've multiplied by 2 on the inside. So the midline is going to be directly between the highest point and the lowest point. Now the highest point on this mathematical wave is given by y equals +1 up here at the peak. And the lowest point is located here at y equals -7. So the question is, what y value is directly between +1 and -7? You might be able to figure that out mentally, but if you're having trouble, remember that you can always average the y value at the peak and at the bottom. If I add together 1 and -7, and then split the difference by cutting the result in half, then the result of that is negative 3. So that's the y value, which is directly between y equals 1 and y equals negative 7. Y equals negative 3 is the midline. Now pause for just a second. Negative 3 is interesting because negative 3 actually shows up in our formula. Negative 3 was the location of the midline, and it just so happens that negative 3 was also the number that was being subtracted here in the output. Okay, with that noted, let's go ahead and figure out the amplitude of this particular sine function. For that, let's look at the distance between the midline and the graph's highest point. The midline is located at y equals minus 3. The highest point is located at y equals 1. So if I count it off, or maybe subtract those two numbers, I can see that there's 4 units between the midline and the peak. So the amplitude would be positive 4. Now 4 is interesting because 4 has actually shown up, once again has shown up in our formula here. Now the number multiplied on the outside was negative 4, and our amplitude happened to be positive 4. So there is a small sign difference between the two values, but they do seem to be conspicuously related to each other. So make a mental note of that. We'll come back to that tomorrow. Let's go ahead and also figure out the period of this wave. How long it takes for this wave to repeat itself. Now I could look at the distance between peaks, and that looks slightly annoying in this case because the coordinates of the peaks are not explicitly shown. So instead, maybe what I will do is I will look at this location here in the center where the graph is passing through the midline going down. And I will follow the wave through one full cycle, down and up and back down, until I reach a matching location where the graph is going through the midline going down. So now that I've found 2 positions on this wave, which have matching behavior and which are 1 cycle apart, let's figure out the distance between these 2 locations, and horizontally it looks like they are pi units apart. So because they're horizontally separated by pi units, because it takes pi units for the period to repeat, that is going to be the period of this particular sinusoidal function. Let's compare the period of this function to the period of the basic untransformed sine function that we got in the previous exercise. The basic sine function, completely untransformed, has a period of 2 pi units. Our function has a period which is equal to 1/2 of that. 2 pi, which is the standard period of the standard sine function, divided by 2. And this 2 is related to the 2 that we're seeing in the input in the formula that we are given. So that is the relationship between the 2 in the formula and the 2 in the period. This is something that we're going to go into more detail talking about tomorrow, which is how the constants in the formula for a sinusoidal function are related to the values of the midline, amplitude, and period. That concludes today's material. Today we briefly reviewed the concept of a transformation, and then we looked at 3 features of a wave called amplitude, period, and midline that we used to match a mathematical wave to a real-world wave pattern.